All right, we're going to do some disk problems here. I want to take this triangle and rotate it around the y-axis. So this is kind of a review from what we did in part 1. So this triangle then would end up over here. Spun around the y-axis. So there's a hole in the middle of this shape. So it sort of looks like it's a cone with a hole drilled through it. So we're going to make a disc slice in it. And when you do the disc or washer method, you slice it perpendicular to the axis. The axis of rotation is the y-axis, so perpendicular to it would be in this direction. And this would actually create a washer and not a disc with a hole in it. And as you can see here, I'm trying to show it, its thickness is up and down, so it's a dy thickness. And we're going to find the volume of just the washer, which is going to be the whole disk minus the inside. The whole disk is going to be like a very short cylinder, only dy high. And a cylinder's formula is the area of the base, pi r squared, times the height, dy. So it's going to be pi r squared dy for the large cylinder, where r, that's the large r, minus the whole, which is going to be pi r squared dy also, but in this case, this is the small r, and this whole thing is the large R. And then we're going to add up all these disks that make this shape, this holy cone, and we're going to add them up from y starting down here clear up to 2. If this is x plus y equals 3 and we move over 1, that's 2. This point is 1, 2. So both of these have a pi, both have a dy, but that's a variable. We're going to integrate from 0 to 2. The y's are going to go from 0 to 2. And we're going to do the large radius, which is in the x direction. So it's x squared from the large radius, which is determined by this line. So I'll call that line x plus y equals 3. That's the equation of that line if it goes through 3 and 3. And this is the x from here minus the small radius, which is also in the x direction. But that radius is always 1. So it's x, but it's also 1 because the equation of this line is x equals 1. So it's the small radius, x squared, but it's 1 squared. So the only problem is this is dy. This doesn't have an x in it. This has an x, so we have to get the x changed to a y, and we can do that by solving this equation for x, and it becomes 3 minus y, so this becomes pi, integral from 0 to 2 of 3 minus y squared minus 1 dy. And if I work that out, 3 minus y squared is 9 minus 6y plus y squared minus 1. that was 1 squared, which is 1, so it's still 1. And if I continue with this, see, 9 minus 1 is 8. And I do the antiderivative, I'm going to get pi times 8x, 8y, because I'm doing y's, minus 3y squared, because it goes to 2 and divide by 2. And this goes to 1/3 y to the third, evaluated from 0 to 2. 0 is not going to create anything, so it's all going to come from the 2. So I'm going to get 16 minus 12 plus 2 in here is 8/3 times pi. So this is 4, which is 12/3 plus 8/3 is 20/3 pi. Now I could have found that by just putting this in the form of 3 minus x quantity squared minus 1 into my calculator, graph it, and then find the area under the curve from 0 to 2. I'll get the 20/3 times pi is here. Okay. Now, I'm going to do a very similar problem. I'm going to take this shape and shove it over 1. So now my equation, instead of x plus y equals 3, is x plus y equals 4. It has that same shape, but I want to revolve it around the axis of x equal 1. So if I revolve it around x equal 1, this point would go to, if it's 1 away from that axis, it'd be 1 away on the other side, which would be right here. And this, that's at 2, will go to 0. And this, which is out here at 4, but it's 3 past this axis, it'll go to 3 back, 1, 2, 3, which is minus 2. And you can tell that that's the same shape as that one up there. So we should get the same answer. But the point of this is, how do we deal when the axis is not the y-axis? How do we deal with that situation? We're still going to make a slice that's perpendicular to the axis of rotation. And so the axis of rotation is this way, so the slice is going to go this way. I'll make it about the same place as we did over there on the top one. So hopefully you can see the inside, and hopefully you can visualize the outside. Okay, so we're going to do the same stuff, large radius squared minus the small one, and the thickness is still up and down, so it's still dy. So I'm going to be integrating, and it's going to be pi large radius. Now here's where you got to be careful. This equation is based on this being 0, 0. The y-axis here is 0, 0. So x in this problem is clear from here out to there, but the large radius is not x, it's x minus 1. So the large radius is x minus 1. And the small radius, well, it's the x is this long, it's 2, but it's 2 minus 1, so it's 1. And the thickness is dy. Now, to get this all in terms of y, we have to solve for x in this, for the large radius, and that would be 4 minus y. And 4 minus y minus 1 turns into 3 minus y. And that quantity is squared. And we have 1 squared. So we're headed to the same thing. Are the limits the same? Well, y is going to start at 0 and go up to 2. So this turns out to be the same integral problem as we had before. 3 minus y is what would replace x minus 1. Because 4 minus y plus 4 minus y minus 1 becomes 3 minus y. Quantity squared. So we'd get the same answer. Now I'm going to do the problem one more time using a method that's not described in the book. So this method we've been doing is called the disk method, or if it has a hole in it, according to the book, they call it the washer method, but it's just a modified disk method. Disk or washer method. Okay? And when we do the disk or washer method, we slice perpendicular to the axis of rotation. Now I want you to look at this same problem and think about this, and think about pieces of pipe. This kind of looks like a piece of pipe right here. Got a hole in it and it's round. And I could take another pipe that's just a little bit bigger that fits over it and make it a little bit shorter, and that would make another pipe here. And then do another one that just fits around it that's a little bit shorter, and keep doing that all the way out, and I could make this same shape with, if I had a whole supply of pipes that were, each one just barely fit inside the other. And each of the larger ones I make a little bit shorter. So I'm going to draw one of those pipes. I'm going to do it in green here. So there's the height of the pipe, and it would show up over here, and it would be a piece of pipe that goes this big around. Okay? Hopefully you can see that piece of pipe. That would be one of the pieces of pipe that would make this shape. There'd be another one that's a little shorter out here, and there'd be some in here that are taller and smaller radius, but that's the pieces of pipe. Now I'm doing the same shape, so I should get the same answer of 20/3 pi. So the thickness of the wall of the pipe is going to be, the thickness of that wall is going to be a dx. And this piece of pipe, if I took my snips and cut it up the side and laid it out, it would be a pretty long rectangle that has a little bit of thickness. The thickness is dx, and the height is this height, which is in the y direction to the curve, so it's y, but it's going to this curve, and since I'm doing dx, I'm going to need it in terms of x, and y is equal to 3 minus x. So the height is 3 minus x, the thickness is dx, and the length of it is the distance around this circle. So what is the circumference of a circle? Well, it's 2 pi r. But r would be from the y-axis out to the pipe, and that's in the x direction, so that would be x. So the length here would be 2 pi x. So this green ring would have a volume that's 2 pi x length times height times 3 minus x times a thickness of dx, and that would be for this one, but I want to add up all those green pipes, and so that would start with x. Since I'm doing dx's, the x starts at 1 and goes to 3, starting with a taller, smaller radius pipe, and working my way out to a much shorter but larger radius pipe. So it's going to go from 1 to 3, the x's are. So I'm going to work this one out and verify that we get the same answer. So we get 2 pi, which can come out, and I'll have the integral of 1 to 3 of x times 3 minus x, which is 3x minus x squared dx. The antiderivative of 3x is 3 halves x squared. The antiderivative of x squared is, and this is minus, 1/3 x cubed, evaluated from 1 to 3, and times 2 pi. So it's going to be 2 pi times, if I put 3 in here, I get 27 halves. If I put 3 into here, I get 27/3, or 9, so I got minus 9. That's putting in the 3. Now I got to put in the 1, minus. If I put 1 in here, I get 3 halves. Put 1 in here, I get 1/3. So 27 halves minus 3 halves is 24 halves, or 12. So these two make 12. Minus 9 is 3. Minus a third is plus 1/3. And 3 1/3 is 10/3 times 2 pi is 20/3 pi. So we can do a ring method or a disc washer method to solve these problems. Okay, so now I'm going to go to a new shape. We've been sticking around with that shape too long. Okay, this time I'm going to make a graph here. Use some of the same equations. I'm going to do x plus y equals 4. So it goes through 4 on the x-axis, 4 on the y-axis. Both intercepts are the same. And I'm going to draw y equals x. And I have this triangle here. And I want to imagine that triangle being over here also. But I'm not going to rotate it that way. I'm going to rotate this around, let's say x equals, see that's 2, around minus 2. Y equal minus 2. Which means this 4, which is 6 above the axis, would be 6 below the x-axis. 6 below minus 2 would be down here at minus 8. And this 0 would be down 2 more below minus 2, which would be at minus 4. And the triangle would be something like this. And this point would come down to here. This point would go from here to here. And now if I have this on it, I hope you could see that this looks like maybe a piece of square metal or plastic or something that's rotated around and could be maybe a bracelet or something. Now, instead of working with the whole bracelet, I'm going to figure out the volume of half the bracelet and then double the answer to keep the problem simpler. Now, I can do this ring method or disc method. I want to do both. Let's first do the disc method, and I'll do that in red. Here's the axis of rotation. The disc method, I always make the disc slice perpendicular to the axis of rotation. So I could do a slice here, which would be a slice down there. It makes a washer. Hopefully you can see that. It would come out here, come around, and go back in there, and go around behind and come out. I could try to sketch this in here, but then it gets a little bit crowded in here. So I'm not going to do much of that. But again, the formula is going to be the pi integral of the large radius squared minus the small radius squared, d something. Okay? So my large radius, well, this is a point on the curve, this curve, and it's up y. So this would be y from this equation, but the radius is going to be longer than that. So the large radius is going to be y plus 2, but this is the y from this equation. The thickness is in the x direction, which says I need to have the equation written in x's. So y from this equation would be 4 minus x plus 2. So I'm going to have, for the large radius, it's going to be 4 minus x, which is the y, plus 2. So over here it'll be pi integral of the large radius, see, 4 plus 2 is 6 minus x. Large radius square. Minus the inside. So now I've got a y that's this. That's in the y direction. But I have to write it in the x direction because the thickness is in dx. And so in this case, the y and x are the same, so it's going to be x is equal to y. So this is y, but we have to add 2 to that. So it's going to be x plus, excuse me, it'll be y plus 2, which is going to be x plus 2. And I would be integrating this from, well, let's see, I'm going to be looking at this in terms of the x's because it's dx. And x is going to go from here to there, 0 to, this is over 2, not 4, 2. And so that would give me the volume of half of the bracelet, and then I would take and double that to get the full bracelet, getting the other half over here. Let's work that one out. So we got 2 pi integral from 0 to 2 of, see, this would be 36 minus 12x plus x squared minus x squared. This would be plus 4x with a minus there, so minus 4x. And this would be plus 4 with a minus, so it's minus 4 dx. So we get 36 minus 4 is 24. No, 32. going too fast. Minus 12x minus 4x would be minus 16x, and the x squareds cancel. 0 to 2 times 2 pi. So this would be 32x minus 8x squared evaluated from 0 to 2 times 2 pi. So I put 2 in there and I get 64. And put 2 in there, I get 4 times 8, which is 32. And if I put 0 in, I get 0. All times 2 pi. So that's 64 minus 32, which is 32 times 2 is 64 pi for the whole braces. 32 pi for half of the bracelet. Okay, that wasn't too bad. At least I don't think it was too bad. You might think it was too bad. Now I'm going to do it with the ring method. So on the ring method, the slice has to be parallel to the axis because we want pipes centered around there. So I'm going to make a slice here. Now on this ring method, the height of the ring is going to depend on this equation half of the time, and then on the other half it's going to depend on this. So we're going to have to do this one. If we do the ring method, we're going to have to do it in 2 pieces. Sometimes the disc method you have to do in 2 pieces, and the ring only takes 1. So there's pros and cons of which method you use. You have to kind of look at the problem and make a decision. But again, slice parallel to the axis. We have a ring. Its height is x, but its thickness is up and down, so it's dy. So we need to do everything in terms of y. So x here is going to be 4 minus y. Down here, when I get to the smaller ones, this is the larger one, which will go clear down to here. Then I'll have some that are in here, but their x is going to depend on this equation, which will be y. So I have these pipes that are in here, sections of pipes, short one. The heights are y here out to here, but up here it's 4 minus y, from here to there. Okay, now for the ring method, again we have this rectangle that's wrapped around to make the pipe. The thickness is dy. The height is, on the large ones, the first ones out here, the outer rings, are going to be 4 minus y. So I got the width, or the height, the thickness. Now I need the length. And that's around a circle, so it's 2 pi r. Well, r is this distance, which is y, but it's got to go to the center. This is y on the equation, so it's y plus 2. That's the r for the big ring. This is the height. This is the thickness. Which is how you find the volume of a box. The length times the height times the width. And we have to add all of those up. Now we're doing y's, so we're going to do from 2 to 4. That would give us just this part of the ring around. Then we have to do the inside part, which is this ring, which is going to be, now the y is going to go from 0 to 2. of 2 pi, the radius on this, it's still up y plus 2, so the radius is still y plus 2, and the height of it now is just y dy. Now, if I work that out, I should get 64 pi if I didn't make a mistake there and I don't make a mistake here. So let's see if I do get that. Okay. 2 pi comes out of this one, it comes out of this one, so it's going to be 2 pi times everything. And then I'm going to have to do, that would be just half of the ring, and I have to do the other half, so I'd have to multiply it by 2. So I'm going to have to take 4 pi times the answer. So if I want 64 pi and I'm multiplying by 4 pi, this in here better be, let's see, 16. I better get 16 from my two integrals, taking the 2 pi's out. Okay, so this multiplies out to be minus y squared minus 2y plus 4y, which is plus 2y, and plus 8. Antiderivative would be negative 1/3 y cubed plus y squared plus 8y. Evaluated from 2 to 4, and so I'm going to get 64 thirds plus 16 plus 32 minus, putting in 2, I'm going to get negative 8 thirds plus 4 plus 16. And then over here I'm going to get, let's see, this is going to be y squared plus 2y, antiderivative would be 1/3 y to the third plus y squared. And I couldn't put these with this before because the limits are different, so I have to work these separately. And so I have to evaluate this from 0 to 2, so I'm putting 2 in here, and I get 8 thirds plus 4. And then I put in 0, and I get 0. And hopefully all of this will become 16 times 4, which should be 64 pi. All right, so let's see what we got here. 64 thirds minus 8 thirds would be, plus 8 thirds and plus 8 thirds. So I got plus 8 thirds and plus 8 thirds and minus 64 thirds. So I've got 16 from 64 be 48 thirds. 48 divided by 3 is 16. So I have minus 16 plus 16. So this cancels that, that, and that. So then I have 32 minus 4 minus 16, but then I have plus 4, so the minus 4 and the plus 4 cancel. So I have 32 minus 16, which is, this is gone now because I canceled it. So I get 16 times 4 pi, which is 64 pi. Ring method was tougher than washer method on this one, but ring method on this was a simpler integral than some of the other ones we had here. So sometimes ring is simpler, sometimes it's not. Now, the book doesn't do the ring method, but I'd like you to know how to do it. So I'm going to ask you, when you do the problems for 6.2, that you do problems 2 and 3 and 4 both ways. On the rest of the problems, you can choose whichever you think might be simpler, ring or disc. But on problems number 2, 3, and 4, do them both ways, ring and disc. I'll be looking for that specifically.